Let's not waste a moment of our time. Let's jump right in here and talk about the equilibrium constant and write some equilibrium constants. So in the last video we discussed how this constant is found in every equilibrium, which most reactions will reach equilibrium eventually, and this constant is just the concentration of the products raised to their coefficients in the balanced chemical equation divided by the concentration of the reactants raised to their coefficients from the balanced chemical reaction. So in short, products over reactants. That is the equilibrium constant. We don't care what the products are or what the reactants are. For the most part, anyway. We will actually talk about a few exceptions to that in a later video. But for now, we don't care what the products are or the reactants are. It's just going to be products raised to their power divided by reactants raised to a certain power. So let's write a few equilibrium expressions here. So this question, or this example, asks us to write the expression for the reaction quotient, which is just another word or another name for this products over reactants. The reaction quotient technically is different than the equilibrium constant, but only because the reaction quotient doesn't necessarily have to be at equilibrium. So the reaction quotient is just this ratio at any point in time, and the equilibrium constant technically is only true at equilibrium. But in terms of the actual equation, it is exactly the same. So we're going to be writing out this ratio for each of these three reactions here. So the first one, we have, actually, well, I'll do the first one, I guess. I'll do the first one, I'll ask you to do the second and third one on your own. So we have 3O2, and it is in equilibrium with 2O3. So the equilibrium constant for this would be products over reactants. O3 raised to the 2 divided by O2 raised to the 3. And that is the equilibrium constant. And also the reaction quotient, if you're not at equilibrium. That's what you would call that. So why don't you go ahead and give these last two a try here, B and C. So go ahead and pause the video and give that a shot. Okay, I hope you tried that, and let's see if you had some success in that. So for B, again, it's just products over reactants. So we would have NH3 raised to the second divided by N2 raised to the 1, which is just to leave it blank. You don't have to put the actual 1 in there. And then H2 raised to the third. And that's the reaction quotient and equilibrium constant. And so then for the last one here, again, we have products over reactants. So we're going to have a bit more going on here. This is going to be NO2 raised to the fourth times H2O raised to the sixth. And that is divided by NH3 raised to the fourth times O2 raised to the seventh. And that's all there is to it. Very, very straightforward. Like I said, we will see a few exceptions to where there are some stuff we don't include in the equilibrium constant, but most of the time it is just going to be take everything from the balanced chemical equation, products over reactants with the coefficients as exponents. So let's look at another example here. This says gaseous nitrogen dioxide forms dinitrogen tetroxide, according to this equation. When 0.1 moles of NO2 is added to a 1 liter flask at 25 degrees C, the concentration changes so that at equilibrium, NO2 is equal to 0.016 molar and N2O4 is 0.042 molar. So part A says, what is the value of the reaction quotient before any reaction occurs? And then what is the value of the equilibrium constant for the reaction? So once again, this reaction quotient, that is just the exact same mathematical equation as the equilibrium constant. It just doesn't have to be at equilibrium. And so before any reaction occurs, all we have is NO2. That is the only thing that we have. So if all we have is NO2, the reaction quotient, which is usually written as capital Q, uppercase Q, that would be products over reactants. But we have no products, because we're not told anywhere in here that we have any N2O4 before the reaction begins. So we would have 0 for the product, and then for the reactant, we would have 0.1 molar raised to the second. But we really don't care about that, because if you have 0 in the numerator, you could have infinity, technically speaking. And actually, if you had infinity, no matter what you had in the numerator, it would still end up being 0, essentially. But no matter what you have in the denominator here, if you have 0 in the numerator, you're going to have 0 as your value for that fraction, or that ratio. So that's before the reaction occurs. After the reaction occurs, when we're at equilibrium, equilibrium constant is going to be products over reactants. N2O4 is our product, so we have 0.042 raised to the 1, and then 0.016 raised to the second. And so if we do that math, let's see. That gives me 164, essentially. That is the equilibrium constant for that reaction at 25 degrees C. Okay, so just a quick note here on the relative sizes of K before we call it for this video. If you're given the equilibrium constant, and you notice that the equilibrium constant is much, much greater than 0, so it's very large, or sorry, much, much greater than 1, I should say. You'll never have any equilibrium constant smaller than 0. So if you have something that's much, much larger than 1, what that's telling you is that your equilibrium, the point where the forward and reverse reactions are equal to each other, it highly favors having products. Essentially what it's saying is you have a whole bunch of products, and it takes all these products for that reverse reaction to be fast enough to match the forward reaction that is working with just a very small amount of reactants. So essentially it's very, the forward direction is favored, is another way of saying that. So it's favoring the forward direction, making more products. You have predominantly products in the mixture at equilibrium if you have a very, very large K value. If, on the other hand, K is much, much less than 1, now again, it will never go negative, but you know there's an infinite number of values between 1 and 0. So if it's much, much less than 1, the reaction is a highly reactant favored. So the reverse reaction is actually more favored. It doesn't take very many products for that reverse reaction to be going just as fast as the forward reaction. So you have most of your molecules in your mixture on the reactant side of the reaction, if you have a K value that is much, much less than 1. And so even without knowing anything else about the reaction, if we just know the overall magnitude of the equilibrium constant, we can get an idea of whether this reaction is favorable or not. So if we have some reaction that we want to perform, and we look up the equilibrium constant for that reaction, and we find that the reaction has an equilibrium constant that is, 1.5 times 10 to the negative 12, which is a really, really tiny number. What that's probably going to tell us is maybe we should figure out some other reaction to get the product we want, because that reaction is not going to give us very much product. Now there are ways we can get around that, and at the very end of this chapter we'll talk about that. But in general, with really, really tiny K values, you're not making much product. It's probably not what you want to use to get the product you're looking for. All right. We'll call it there for now. In the next video, we will talk about a slight variation on the equilibrium constant that uses gases instead of concentrations. And we'll talk about when these two things are actually the same, and we don't have to worry about it, and the situations where we do have to worry about when the Kp, as we'll talk about next time, and Kc are different. So I'll see you in that next video.